All right, this time for real, we're gonna do assembly programming for the Atari 6502 CPU. We're emulating an Atari 800 XL, and we're reading the book Atari Roots. Let me show you where that is. Here we go. So it's online. You can, the links will be in the description for the VOD, but it's atariarchives.org/roots. And you can kind of, there's a series of this if you look for it on YouTube from me, where we've been going through this. And we're on chapter 5 now, dealing with, chapter 6 now, doing the right address. We've gone through a bit of this. I would actually say most of this. And now we're up to indirect addressing from the last video. So we looked at this, we looked at all of this. Here, we're up to this part. But instead of using this nicely formatted OCR document, I'm using the PDF here. So this is from the original document here, and it just looks a little bit more authentic, so I'm using that instead. All right, so I don't think there's much else to say about it, so we can get started. From the last video, we looked at this subroutine, and it didn't work for me. Like, I couldn't figure out what was wrong. And then we got a really nice feedback comment from Chuck. Where was that? So it's in the 6502 list. The last one, right? So that must be here. And where do we see the comments here? Where are you comments? I guess I don't know how to use YouTube, or maybe it's just because I don't see the comments because it's me. That's so funny. What the hell? Oh, here, 3 comments. Here we go. Here it is. The data move routine did not work properly because what is stored at address 600 is a string and the routine code only starts after the string ends. The .byte directive simply places bytes in the memory one after the other. It's up to you to decide if they are meant to be interpreted as code or data. I'll explain this if you're getting lost in a minute. I'm just going to keep reading. What happens when you tell the 6502 to start executing code at 600 is that it will interpret the characters of the string as instructions, which for all practical purposes is garbage. Atari Roots seems like a good book so far, but I think this example doesn't help the reader very much. Doesn't seem like it explains anywhere that after you assemble a program, Max65 will print the address of all the labels it contains, so you're supposed to start executing at the address that is displayed for the routine name. An alternative to this would be, to always put the main routine at the start of the... Oh, you guys can't see what I'm reading. I'm really failing today. Really failing. An alternative to this is to always put the main routine at the start of the listing so there's no ambiguity as to where in memory it will end up. In this particular case, the string could be placed at the end of the listing, right after the RTS opcode and before the end directive. In the case where the program worked properly is likely because the string was very short, so it only executed a few instructions that didn't make branch somewhere else in our memory nor stomp the string. You could confirm this by stepping through the program, right? So what that means is that in our example program here that I loaded in, it was failing, right? And if you look at this, over here we have text. This says that the program's going to start in memory address 600. So all the code starting from here on is going to be in memory address 600 and on. And there's a label here called dat move that comes after this string. This is the byte representation of some string, and in this code it's basically looping. and making a copy of this buffer of characters into memory address 5000, because you can see here that it first loads from text this label with X as its incrementer, and then it stores it in memory address 5000 with the same increment. So 5000 first, and then as it loops, 5001, 5002, etc. But the problem is that when I was running this, I was running it from the very beginning of the program, which is 600. But 600 has just these various like random garbage strings that we're trying to copy. It's not garbage strings, it's strings, but it's not code, right? But really, the code execution should start at dat move, right? So I didn't have that in mind because I didn't understand that was important. So let's start this session by first trying to fix our code that we did from last time. That is, you see here, I made a dat move to dot source. That should be this program listing here. So let us load up max 65 420, and this will be the this is the assembler, and then we're going to load this code dat move to dot source. And now if you see it, you basically see the same code that we were looking at on this other PDF screen. The only issue here is that in line 150, where the actual code starts, there's no label, right? Over here on the PDF, you see dat move, but we have no dat move here. So instead of like making it on its own line, I'm just going to combine it with this clear decimal mode, or I can't remember the exact name, but we're going to make it dat move here as a label. It's only one space if it's just a label. And then we still leave the CLD in here. So now when we look at the code, we have the byte string here. And then in 150, we have the dat move label. And now I should be able to assemble it with ASM. And now we have the code. And we need to keep track of this dat move label here. It printed out all the labels, just like Chuck said. And I think it was Chuck. I don't know. I don't know who that user is, but that was really helpful. And so 618 is where the code starts, the actual code. And 62A is the last instruction you see over here. So we know that much also. So now we can quit out of this CP for command processor. Anyway, it's basically DOS. And now we can run debug 65. No, it's just bug 65. Bug 65. That beautiful sound. And now we can look at 5000 where we're going to copy this stuff to. You can see that it's all empty. And we can look at also 600 where the code, you see, like we can actually see the string code here. And 618, that's where it started, right? Our code. And this is like the CLD and all of that instructions. So now what we can do is actually run the program. So we say G for go, I think, for execute. And we start at 618. And we're going to end in address. We're going to put a breakpoint in 2A because that's the last line of that code. So great, this is the current state. The accumulator, the X is the X register, which we've incremented to 17. And now if I print 5000, we should see the words that it copied, right? Before it was all zeros, and now it copied what was here in 654.41. Now it's in 5000. And it says, take me. I think it's longer than that. Let's look. This is this is 0, 1, 2, 3, 4, 5, 6, 7. So the next one would be 8. So we do D5008. Take me to your, so if we add another 8, it's 16. And 16 in hexadecimal is 10, right? I think so. Take me to your leader. So that is, I think that's the end of it. Yeah, the rest is dot, 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 and so forth. So that's really, that means it's not initialized. They're all zeros. And that's probably about 17 letters, right? Uh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Oops. I wonder why this 17 was here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Looks like that is a bit off. I wonder. Oh no, it's 17 in hexadecimal, right? Yeah, so it's 16 plus 7, which is 23. And that matches up a lot better. All right. So we fixed the program that we had last time, and now we can go straight into indirect addressing. Hold on 1 second here. Let me make sure this is working. Yep, looks like it. Do you guys hear me? Is it for the people that are on? Can you hear me? Is everything working? I'm gonna be going away for a few days, so there won't be any streams or anything for a little while. Holidays are always tough. All right, let's get started with indirect addressing. There are two subcategories of indexed addressing: indexed indirect addressing and indirect indexed addressing. Does this feel like how much wood can a woodchuck chuck? Okay, let's try to read that again for my dyslexic brain. There are two subcategories of indexed addressing: indexed indirect addressing. Okay, so it's indirect, and indirect indexed addressing. So they're just switching the word indexed indirect, and the other one is indirect indexed. Doesn't that sound like, why did you make life so hard for me? Okay, both indexed indirect addressing and indirect indexed addressing are used primarily to look up data stored in tables. I swear this could be like a dream. You ever have dreams and you're like, that made no sense. How did I think I was awake? You know, this is like one of those things like, I'm reading garbage. Like, how can this be real? Who would call it these things? But no, it must make sense. So we'll go on. If you think the names of the first two addressing modes are confusing, you're not the first one with that complaint. I never could keep them sorted out myself until I dreamed up a little memory trick to help eliminate the confusion. Okay, great. We're not the only ones. Here's the trick. Indexed indirect addressing, which has an X in the first word of its name, is an addressing mode that makes use of the 6502 chip's X register. Okay, so that means it uses the X register. Indirect indexed addressing, which doesn't have an X in the first word of its name, uses the 6502's Y register. Wouldn't it be easier if it was called indirect addressing X, indirect addressing Y? Now we'll look at each of your Atari's two indirect addressing modes, beginning with the indexed indirect addressing. It does help because now I know that indexed indirect addressing is going to use the X register. Format: ADC, some memory address in hex, and X. Indexed indirect addressing works in several steps. First, the contents of the X register are added to a 0-page address. Right, so this is only two characters in hexadecimal, so it's in the 0 page. So what does that mean? It can be up to 255. Are added to a 0-page address, not to the contents of the address, but to the address itself. Okay, so it's going to take the address and it's going to add X to it to kind of like jump forward in the address, which makes sense, right? The result of this calculation must always, hi there, oh, I can't say your username. E3060 E1E, hi from Czechia. Hello. Hello from France here. Bonsoir. All right. Where are we? The result of this calculation must always be another 0-page address. When this second address has been calculated, the value that it contains, together with the contents of the next address, make up a third address. Oh my God. When the second address has been calculated, the value that it contains. Oh, so we're going to get we're going to look up the value in that address together with the contents of the next address make up a third address. It's going to look at the contents, it gets another address, and then it looks at that address and the next address to come up with a third address. That third address is at last the address that will finally be interpreted as the operand of the statement in question. Okay, so this is pretty indirect. I get why they say indirect. An example of indexed indirect addressing. An example might help clarify this process. Yes, that would be helpful. Let's suppose that memory address B0 in your computer held the number 00. So that's really 0, right? That memory address B1, let's suppose that. Okay, here's the two that's. We're supposing that memory address B0 is 0 and that B1 has 06. And that the X register held the number 0. Here are those equates in an easier to read form. Here's B0 is 00 and B1 is 06 and X is 00. Now let's suppose you are running a program that contained the indexed indirect instruction LDA B0X. If all those conditions existed when your computer encountered the instruction LDA $B0X, your computer would add the contents of the X register, a 0, to the number B0. All right, so both of them would be 0, right? Because B0 is 0 right now and X is 0. The sum of B0 and 0, of course, be B0. It's not looking in B0. It's just adding the address B0. Okay. So your computer would go to the memory address B0 and B1. Well, how does it know about B1? It would find the number 00 in memory address B0 and the number 06 in an address B1. I see. It's just going to add 1 to the first thing here. Okay. So the first thing it does is it adds the two together, b0 plus x, literally b0 plus x, and then we get b0 because x is 0. And then we go to b0 and b1 together, and we look inside that memory. And in b0, it finds 0, 0, and in b1, it finds 0, 6. So I'm guessing it'll be 0, 0, 0, 6. Since the 6502 base computer stores 16-bit numbers in reverse order, low byte first IC, so it's going to be 600, your computer would interpret the number found in B0 and B1 as 600 hexadecimal. So, and we've been using 600 a lot, right? That's where we always start our programs. So it would load the accumulator with the number 600, the 16-bit value stored in B1, B0, and B1. All right, so it's going to have an address in the accumulator then? Yeah. The accumulator is going to have this address 600. Now let's imagine that when your computer encountered the statement LDA B0X, the X register held the number 4 instead of the number 00. All right, so now we can figure this out, right? Let's figure it out before they tell us. Can we do this without writing anything down? So we're going to see LDA B0 comma X, except X is the number 4. So it's going to add B0 and 4 together, which will give us B4, this address here. So then it's going to take B4 and B5 and reverse create the address. It'll do 1CFC, and that value 1CFC is going to be loaded into the accumulator. There it is, 1CFC. Now let's actually read. If these conditions existed when your computer encountered the instruction LDA B0, X, your computer would add the number 4 to the number B0 in hex, and would then go to memory address B4, because when you add the two together, you get B4. And then it takes B4 and the next address, which is +1, so that's B5. And in those two addresses, it would find the final address, low byte first, of course, of the data it was looking for, in this case, 1CFC. So the final address is based on what is inside the memory address that we figured out. All right, so that kind of makes sense. So in here, we'll have a memory address in the accumulator. A rarely used mode. Oh, sorry. Sorry for the pause. A rarely used mode. Sounds almost creepy, right? Indexed indirect addressing is not used in many language programs, in many assembly language programs. When it is used, the purpose is to locate a 16-bit address stored in a table of addresses stored on page 0. Since space on page 0 is so hard to find, it's not very likely that you'll ever be able to store many data tables there, so it's not too likely that you'll ever find much use for indexed indirect addressing. All right, well, I guess we learned what this is, but it's not used a whole lot. Now we're going to learn the flip of it, indirect indexed addressing, which is with Y. Notice here, the parentheses are around this address, and before the parentheses were around the whole thing. So basically it's saying this probably means like, here, take this address and then like change the address with X and load the accumulator with that. Or this is add with carry. But over here, the address is here. So it's probably going to read whatever is in the address and then just add Y to its value. Anyway, let's see. Indirect indexed addressing is not nearly as rare as indexed indirect addressing. So maybe they should have started with that. What do you guys think? In fact, it is quite often used in assembly language programs. Indirect indexed addressing uses the Y register, never the X register. You need a scissor? You're welcome. Is that for dessert? But not for, this is for later, right? All right. And never the X register as an offset to calculate the base address of the start of a table. The starting address of the table has to be stored on page 0, but the table itself doesn't have to be. When an assembler encounters an indirect indexed address in a program, the first thing it does is peek into the page 0 address that is enclosed in the parentheses that precede the Y. The 16-bit value stored in that address and the following address are then added to the contents of the Y register. The value that results is the 16-bit address, the address the statement is looking for. So it's going to take up 2 bytes in your 0-page table, your address memory, page 0 memory. Let's take a look at the example. An example of indirect indexed addressing. Here's an example of indirect indexed addressing. Your computer is running a program and comes to the instruction ADC, add with carry, B0, comma Y. It then looks into memory address B0 and B1, and in B0 it finds the number 00. And in B1 it finds the number 50, so it's obviously going to be 5000, which is the other address we've used in the past. And the Y register contains a 4, so it's going to become 5004. Here's a chart that illustrates those conditions. Here it is. B0, 00, B1, 50, Y equals 04. If these states existed when your computer encountered the instruction ADC B0, comma Y, then your computer would combine the numbers 00 and 50 and would come up in the 6502 chip's peculiar low byte first fashion with the address 5000. It would then add the contents of the Y register, 4 in this case, to that number and would wind up with a total of 5004 hexadecimal. That number, hexadecimal 5004, would be the final value of the operand parentheses B0, close parentheses, comma Y. So the contents of the accumulator would be added to whatever number was stored in memory address 5004. All right, so that's pretty cool. Once you understand indirect indexed addressing, it can become a very valuable tool in assembly language programming. Only one address, the starting address of a table, has to be stored on page 0, where space is always scarce. Yet that address added to the contents of the Y register can be used as a pointer to locate any other address in your computer's memory. As you become more familiar with assembly language, you'll have many opportunities to see how indirect addressing works. You'll find a few examples of the technique and programs in this book, and you'll run across many more examples in other assembly language programs. I'm like really tempted to try to use this, but I'm not sure how useful it actually is to do that. I think if we like try to actually program that, we have like here we load the x to 0. I imagine we can load this y with like a number 4. And then we can like copy something. But should we do it? All right, let's do it. It just takes a little bit of energy to like to want to do it. So should I write on paper a little bit first? All right, so we're going to use the same thing here for page 0. What are these guys using here on page 0? They're using B0 and B1. Let's imagine that that's actually safe to do. And we'll have to put stuff into B0 and B1, right? So well, I think the only way I know how to do that is to put it in the accumulator. So load stuff in the accumulator and then store it into B0 and B1. The other thing we can do is just like this byte thing here, text byte. I bet we can just put like byte strings in here. Yeah, I bet we can just put data in here. No, but that's in address 600. We can't do that with B0 and B1. All right, so we're going to load the accumulator, and then we're going to store stuff there. And then what we need to do is we need to set the y to 4. So that is done by LDY, I think, number 4. Which means it's going to come up with the address 5004. And then we're going to, so we should put a number in 5004 also. So we need to 5004, put a number. And then we can just run add with carry, I guess, right? So let's see if we know at all what we are doing. Here we go. All right. So the first thing we do is we tell it that we want it to say, this is a compiler directive, to store the program into memory after it's assembled. Then we want to tell it where to put the stuff in memory address 600. And then we said, yeah, we have no data here, so we can just we don't need this. Like in the last time, remember we had to put the dat move, but we don't need to do that. Now let us load and store the accumulator. So we'll put in the accumulator the number, we want 5000. So the very first number should be 00 and then 50, right? So load 00. That's how it works, right? And then we store the accumulator into memory address. We said B0. Oh, I didn't do the decimal binary mode thing. It seems like that's always a good idea. Good idea. So that is CLD to clear the to make it really, in case we're doing arithmetic. I don't think it matters, but it can't hurt, right? Okay. So now we're going to then load the accumulator with the number 50. And then we store this into B1, right? And we should initialize the Y register with an, oops, crap. We initialize the Y register with the number 04, right? 4. Which means that when it tries to... Oh, and what was the command to actually look it up? All right, so we've set up the 4, but we need to put something in 5004 also, right? Because it's going to load that. So we should probably put something in 5004. So let's load the accumulator with the number, we love the number 2. And then we're going to store that in 5004, right? I think this works. And then after that, we're going to, the stage is set, and we now can do add with carry. Yeah, so it's good that we put it into decimal binary mode. B0, comma Y. And now the value in there should be 2. But what's it going to add? Add the accumulator. Oh, the accumulator has what in it? We should preload the accumulator with something. So let's do load accumulator with the number 5. So it's going to load 5 and it's going to load 2, right? Are you guys following this? So first we're setting up B0 with 0, B1 with 50. Then we're setting the Y register with 4. And then we're loading the accumulator with 2, and we put that in 5004. That's where the indirect address will eventually be, right? And then we load the accumulator with 5, and then we're going to add with carry, so it's going to take the 5 in the accumulator, and then indirect access this, which gives it address 5004, and 5004 it's going to find number 2. So it's going to add 5 and 2, and we should get 7. So I'm just going to write down 5 plus 2 equals 7, so I don't forget. And then we tell it return from subroutine, and then we say end. Let's save this before we compile in case it totally crashes. And that is called list. I know that Chuck told us to use save, but let's do that next time. I think when we just have the source code, we can use list. And we'll call this indirect indexed addressing dot source. I better write this down. IIA dot source. All right, so that should have saved it on disk. And now let's try to assemble it and see if it works. All right, great. Oh crap, I made RTS, I indented it wrong. 200 space RTS. Okay, that looks better. All right, so it has no symbols. It starts in 600 and ends in 614. 600 to 614. So now let us try and go to DOS. We'll go into our bugger. And we're going to print all of these things. So B0, you can see that it has, oh, it actually has a number in B1. This is a little disconcerting because it has 5 in there. I have no idea what that's used for, and that could screw us up. That looks like it's the number that we want to put in because it's 5,000, right? It's kind of weird, right? It's already set to that number. And then 5004 is where we want our actual me to y. Oh, this is your take me to your leader. We still have that code in there. I'm betting we fixed it by overwriting the stuff. Anyway, so display 5000 has take me, right? And 5004 is the space, but eventually 5004 should have the number, whatever we loaded there, 2 or 5, and I think we can run it. So we do G 600 at our breakpoint is 614. And accumulator is 25. That's not what I expected. So let's look at 5004. We have a different thing here, which is 02. Yeah, I think I put a 2 in there, right? And then the accumulator should have, I don't know why it has 25. Maybe I did my math wrong. The 2 is correct for sure. And we got to line number 614. Let me see here. We load it again. What do we call it? IIA.source, right? Clear, load 0 into this, then load 50 into B1. Why don't we just like break at 160? Sorry, whatever 160 ends up with. So let me restart the computer because we had kind of screwed up memory, right? And then let's load this again. Enter. Okay, so we have this code. Now I can assemble it. And we are going to stop at, where was it? Let's make it stop at load, store, break here. We'll break at LDY, so 160, we'll call it B1 for break 1. LDY number 4, right? And so we're going to break at 0609 that you can see over here. And we'll see what our status should be. It should have in 50, in B0, it should have 00, and B1, it should have 50, right? It should be 0050. Let's make sure that that is correct. So this is compiled, and now we can go into the bug 65, and now we can look at 50, and you can see it says 00. The next one is 03, and that's not what we want, right? We want 0050, but we haven't run our program yet, so let's go ahead and do that. 600 with a break at 0609, or just 6, oops. Go 60 at 609. Alright, so now when I look at 50, I have 0050. Oh, wait a minute. Oh, this is 50. 000D. I have a feeling I'm inputting these numbers wrong. I bet it needs to look like this. Foreground. D1 IIA dot source. So I bet in here when we store it, we need to store 130 needs to be store in hash $B0. No, that's not right. Store accumulator into B0. It's the load that we want. It's the load. Let's look at this again. So the load is, this is correct, but here, this is a memory address, but we want to, sorry, here, the 50, we want it to be hash $50. I think to say that we want to store the literal hexadecimal number 50. So let's try that. Number $50, just like it says here. I guess at the same time, it won't hurt to say load for 120 the same thing with 0. Just do like $00, right? Just to be safe. And this load 2 I think is perfectly fine. And I think the load Y is perfectly fine also because it's loading, it's not trying to manipulate a memory address, I guess. It's a little unclear to me, but let us save this. IIA2.source. And now let's, we've assembled it. Oh, we've lost the breakpoint. Let's have the breakpoint again. That was in the LDY, so it's at 160, 160 space. What do we call it? I think B1 for break 1, nothing to. And then we have LDY number 4. There we go. And now when I compile this, I have 0609 as the address for the first breakpoint. Let me save this again. I think it will just overwrite it, right? Oh, that's not enter, it's list. Oops, almost really screwed up. List is to print, right? Yeah. Alright, that saved it. Now I've assembled it for sure. Looks good. I quit back in here and I run bug65. Now when I display address B0, it says 00, but not, oh yeah, and it says 5 in there. Well, did we have that last time? And then in, well, let's try running it. G600 at 609. That's our breakpoint. Okay, we got 50 now. That's interesting, but we didn't add anything, right? So B0 has 0050, and X is 0 and Y is 0. So now the next breakpoint should be the next number where we actually load the Y register. So I should be able to do G600 at 660A, because that would be the one instruction after 609, right? Oh crap, I screwed it up. Let's restart. I don't know what I screwed up. I thought that made sense to me, but I guess not. Enter D1 IA2 dot source list. We had breakpoint 1 here. That all looked right. And then I thought I would do breakpoint 2 at 70. There's probably a way to do like step next and everything, but I don't know how to do that. So that means when I compile this, the next one is, oh, they're 2 bytes. That's why. So it's 60B is the breakpoint. And after that, it should have the Y register set to 4, right? Because the next one, the Y register is set to 4. So when we break, we should see the Y register set to 4. Let's try running that. Go 0600 at 060B, right? And the Y register is set to 4, so that's good. We're getting closer. Instruction, load number 2. How in bug 65 do I go forward? Is there like a help? What does this mean, help? Okay, so we're gonna have to look for bug 65, a bug 65 manual, because I have no idea how this thing works. Do I have a book on bug 65? I wish Atari Roots told us this stuff. Well, I'll have to write a little note to myself. Find bug 65 manual, because not being able to step through this. Maybe next. Yeah, that doesn't work. Strange. Hey, Findus, how's it going? But anyway, we're trying to debug this. Maybe the whole program works now, so let me just try running the whole thing. And it was 0614 was the end. Hey, it has the 5 plus 7, 5 plus 2, 7. So we worked. We worked. So we should see that in B0 we have 0050, right? And in 5004 we put the number 2 in, 5004. We put the number 2 in there, right? So you see that. and then the accumulator had added them both, right? So does that make sense to you all? Like, I hope that makes sense, but I'm happy our program worked. Um, Super cool. So we actually did indirect indexed addressing. There's probably a much better way of, doing it, but I don't know it. And this is why the streams take forever to do a few pages. Like in other languages, when you see a new command, you test it out, it takes like, a few minutes. But here, it's like an ordeal because it's assembly and it gives, like, if it doesn't work, it doesn't give you much help. It's probably, yeah, it's crazy how much more helpful modern compilers are compared to assembly. Assembly assumes you kind of know what you're doing. All right, so where are we? We just did this. This is what we just did. We had B0 with 00, B1 with 50, and Y register with 04. The thing to remember is when you are putting addresses within memory, you need to put the $sign in front. They probably talk about that a long time ago. Well, let's see. We're on page 105. Let's see if we can find where they told us that. Actually, it'll be easier to find that in the browser, I'm sure. So, inside bytes binary, let's see, maybe it's in here. Let's see if we can find where. No, this is still like they're just writing basic here. So that's definitely not it. Inside the 6502, probably not. Okay, this is immediate mode, right? Oops. Interpreted as a literal number, not the address of a memory location on your computer. As you can see, the memory address that follows the instruction STA is $CB, the hexadecimal equivalent of the decimal number 203. Since there is no number sign in front of the hex number CB, your assembler will not interpret CB as a literal number. Instead, CB will be interpreted as a memory address, which is what a number has to be in assembly language if it is not a literal number. Incidentally, if you did want your assembler to interpret CB as a literal number, you would have to write it hash $CB. When we found it, huh? When the number symbol and a sign appears before a number, it is interpreted as a literal hexadecimal number. Okay, got it. So if we just have the hash sign, it means it should have said here that it's a number, a literal number, but in decimal, I'm guessing. Whereas hash $sign means it is a literal number but in hexadecimal. So that makes perfect sense why when we are doing our code, where was it? It was like page 105, right? Yeah, that in here we need it because we're actually storing a hexadecimal number as an address, as a memory address into this memory address, right? So if we just have it, what I had before was just number sign, which means I think it treated it as 50 or 00. And that's just bad because we're not storing the number 50. We want the hexadecimal number 50, which is totally different. It's like, yeah, 16 times 5. All right. We've understood ourselves. Did we read this already? Yeah, we did. Now we're up to indirect addressing. Okay, so it's unindexed indirect addressing. So this is like without the X, without the Y. So it's not indexed indirect addressing and it's not indirect indexed addressing. It's just indirect addressing. Honestly, it would seem to make sense to like basically start with this. Like if I wrote the book, I would have started with this because it's the most basic one. And then you add the X and you add the Y. Or maybe you add the Y one first and then the X because the X one just, doesn't make too much sense. Yeah, it's not a compiler. It's like a translator. It doesn't really know much. Yeah, it's kind of crazy, especially given the fact that like when you're programming on these 8-bit computers, it doesn't even have a sense of like one program being separated from another. So it can like totally stomp on stuff that a previous program was doing or something. It's like just memory. It's like whatever. It's like you let someone, like you put your apartment on Airbnb, someone uses it, like they might not put everything back the way you expected it. So the next program runs and things are just like, in garbage everywhere. It's kind of crazy. All right, indirect addressing. In 6502 assembly language, unindexed indirect addressing can be used with only one mnemonic, jump. All right, well, that makes it easy. One example of unindexed indirect addressing is the instruction jump 5000, which means jump to the memory location stored in the address 5000 and 5001. All right, so basically, since each memory location can only hold 8 bits, it looks at the next two memory bits and combines them together, probably in reverse order, assuredly, because that's how all the other ones did it. And then it jumps to that address. We're not going to write that because, well, we literally could write this, right? I just don't want to. Yeah, I don't want to because I don't know how to start a new, like, hey, I want this part of the program stored somewhere else. So the only thing I could do is jump. Well, I guess I could put some random data in the middle and then make a label and then jump to that. No, let's not do that. Should we do that? No, let's not do that. I'm pretty sure I can do it. So let's not do it. If you guys really want to see that, then like leave comments or say something in chat because otherwise I won't do it. But if you want it, I will definitely do it. The LIFO concept. The stack is what programmers sometimes call a LIFO, last in, first out block of memory. It works like a spring-loaded stack of plates in a diner. Wow, these examples are kind of old because like spring-loaded stack of plates in a diner, like first of all, diners exist mostly in the US and in other places that doesn't really exist. And then spring-loaded, like that feels kind of old. So yeah, it's a kind of bad example. Where I see these spring-loaded things a lot is in airports when you like when you go through security check before they put your things through the X-ray or whatever. You got to get those like bins, right? And a lot of times those bins, like at the end or in the beginning, they kind of like pop up like this sort of like conveyor belt of bins, and they're kind of like spring-loaded or I don't know what they use. So I kind of like imagine that. But anyway, either example, pretty bad. But anyway, let's move on. When you put a number in the memory location on the top of the stack, it covers up the number that was previously on top. So the number on top of the stack must be removed before the number under it, which was previously on top, can be accessed. Wow, that's like a hard way to say it. But basically, it's called a stack because things stack up, right? So if you have a pile of any kind, like of books or something like that, and the thing about stack is you can only look at what's on top. So if you make a stack of books, right? So let's say you have 3 books on it. You have War and Peace, and then you have the Dubliners, right? And then you put on Hunger Games, right? So before you can access the Dubliners, you have to then take off the Hunger Games, and now you can access the Dubliners. And then if you take out the Dubliners, you can start reading War and Peace. Yeah, those are the books I read. No, just kidding. Well, not sort of. I don't know. Let's not talk about. Let's move on. There we go. How 6502 uses the stack. Okay. The 6502 processor often uses the stack for temporary data storage during the operation of a program. When a program jumps to a subroutine, for example, the 6502 chip takes the memory address that the program will later have to return to and pushes that address onto the top of the stack. Then, when the subroutine ends with an RTS instruction, the return address is pulled from the top of the stack and loaded into 6502's program counter. Then the program can return to the proper address and normal processing can resume. The stack is also used quite often in user-written programs. Here is an example of a routine that makes use of the stack. You may recognize it as a variation of the 8-bit addition program that we've been using. Before I forget, I want to think I want to add something to our cheat sheet. Right. So I wanted to add that in general, label the beginning of your program, which is after any data parts. When after assembled, you'll note the address of this label. That is where your G command that is what passed to the G command to start your program. That was the mistake we had last time, so I think that is useful to know. All right. B save instead of save. I forget the difference between B save and save, but oh, here it is. Yeah, so what is save then in? We'll have to look that up later, but let's not get too sidetracked because my ADHD can get pretty bad, and next thing we know, we're like totally doing something else. Time goes by so fast when I'm doing this stuff with you guys. I know it's not like I say you guys like there's like hundreds, but no, I know we don't have many. Oh, we have a few people who aren't talking. Hi, Findus, anyone else out there? But like I just get lost. In the beginning, if you were here in the beginning, I'm always like, oh, when I start these things, I'm like, all right, let's go stream. I don't really want to do anything. But then once I get started, it's like, oh, I don't want to stop. I could just go on and on. It's really like, otherwise it's just like my posture and like talking too much that causes the problem. But like, I think one stream was 6 hours, and afterwards I was like, it felt like an hour. All right, so here we are. 1. An addition routine that makes use of the stack. Why is there a little 1? This little 1 is a secret. Don't try to run this program until you understand the stack and how to prevent the program from crashing. don't. Don't you hate it when someone tells you don't? All right, so here, these are comments. This is where the program starts in memory. Stack add. This looks like a label, right? So this starts the program. They didn't put a command after it just to be simple. This is to clear the decimal stuff. Too much food during Christmas, LOL. For me, yes, but that's not why I was tired. I was tired because it's like I had lots of obligations to see people, to do things, and then also like I said I'm going to go out for a few days after this, more traveling, so we have to prepare for that. We have to pack our bags. Like it's just a lot. Um yeah, and then outside is a lot more people. So, just the autism doesn't like too much sensory stuff, and like there's so many people in the stores everywhere. It just gets just so fatiguing. Yeah. So let's see. We are setting to binary mode, clear the carry flag. Oh, I didn't do that last time in my other program. That's probably why it screwed up a little bit. Stop! We were using 2, right? Yeah, we don't clear. If we're going to add stuff, we have to clear. So let us clear the carry flag just in case, because otherwise it could be really screwed up. All right, so here it is. We're not going to run it again, but we will save a new version. And we do that by running list. Wait, was that 1 or 2? That was 2, right? Yeah, I think this is 3 now. All right. So we have IIA3. 1 free sectors? Does that mean we filled up this disk? Oh my god. I bet I can erase a few of these things. I don't need like all of these different versions of this stuff, right? Bug 65 is huge. What's bug 3000? Remember I said I can get ADHD? Bug 65 version 2.0. But isn't that the same as bug 65? 2.0. It's the same thing. Bug 65 COL. Color? I don't know. It's still bug 65 2.0. And what is bug 65 v4? It still says 2.0. Like, there's no difference in the version number. It's weird, right? But the size is different, so who knows? Anyway, it probably doesn't affect us too much. Okay, let's come back to reality. We are trying to do something. We're trying to understand this program. Okay, so we clear the carry flag, then we do PLA. Did we learn what PLA meant? Maybe here. Does this have like commands? Editor commands. Oh, this is the one that had save, right? 64. And then we also have binary save and save. All right, we're getting lost again. but it's okay. It's all for a good cause. Enter, find, where save. Load. It was page 22, which is like here somewhere. Here. Saves the internal tokenized form of the user's in-memory text source to a disk file. Save will save the tokenized user source file to the specified. The format is as file header for. All right, so it's kind of like enter, but just tokenized. Why did they tell us to use? Sorry, it's like list, except it's tokenized. I wonder why they told us to do that. Didn't tell us to do that. So, and then we use load. Load will clear the user memory before loading. Hey, that's pretty useful. So maybe we should just use load and save. I saw enter here somewhere, right? That doesn't matter. So why was I here? Can't remember a thing. Do they have a list of commands? No, they don't have a list of commands. Major added address modes. No. New memory. So they don't have like a list of it. Anyway, it's probably in here. So we're on page 107. Let's see if we can search for PLA. PLA. Oh, it's really slow. We need a resource where we just have a list of all the opcodes. So I'll find one for that. Find resource of all opcodes. 6502 opcodes. PLA 24. Oh well, that was pull the top value off the stack and deposit it in the accumulator. All right, so it's like pull to the accumulator. Add with carry B0, store C0, return. All right. The program is a simple, straightforward addition routine that shows how easy and convenient it can be to use the stack in assembly language programs. In line 110, a value tells us a value is pulled from the stack and stored in the accumulator. But when it starts, there's nothing in the stack, right? Okay. Then in line 120, the value is stored in memory address B0. So, okay. In lines 130 and 140, another value is stored from this is pulled from the stack and added to the value now stored in B0. This is my usual time to play D&D, but I think we canceled this week. That's my alarm that goes off to remind me. All right. Added to the value now stored in B0. The result of this calculation is then stored in C0, and the routine ends. That's only one short example of many ways in which the stack can be used. You'll find other ways to use the stack in later chapters of this volume if you take care to manage the stack properly. In other words, if you clear the stack after each use, it can be a very powerful programming tool, but if you mess up the stack while you're using it, you're surely bound for trouble. Mnemonics that make use of the stack are PHA, push the contents of the accumulator onto the stack. What's the H? Push. I see. Push. Push the contents onto the accumulator. Pull the top of the accumulator of the stack into the accumulator. Push the contents of the P register onto the stack. pull the top value off the stack and deposit into the P register. JSR, put the current PC on to the program counter. That's where we are in the program, I guess. Um, Memory address. On the stack and jump to address. RTS, pull the return address off the stack and put it in the PC and increment it by 1. This will cause execution to continue where it left off. I see. So you don't always have to use the stack um, for remembering your program execution, your memory address. Here, we're going to be using the stack to like just to add numbers. But then the question is like, we need things to be put into the stack for this to work, right? And I don't see where that is happening. Like we would need a few PHAs or something like that. Yeah. All right, the PHP and PLP operations are often included in assembly language subroutines so that the contents of the P register won't be wiped out during subroutines. When you jump to a subroutine that may change the status of the P register, it's always a good idea to start the subroutine by pushing the contents of the P register onto the stack. Then just before the subroutine ends, you can restore the P register's previous state with a PHP instruction. That way the P register's contents won't be destroyed during the course of the subroutine. So if you are like me, you're like, what the heck is a P register? We're on page 108. We're at the end of the chapter, but let's remember what that, actually is probably easier on the browser. So P register, that would be inside the 6502. And we can see in here, there's this P register here. ALU, program counter PCS, processor status. Okay. It's called the processor status register, usually simply the status register, but abbreviated P. Sorry, I know it's so small, but this site doesn't. Let's see, what page is this? Does it tell us the page? It is right. We can find this in this. We can certainly find this in here. 43. So it'll be around 43. Here we go. Here, I just read this, and then we are looking at it. The processor status register of P is a little bit different from the other registers in the 6502 microprocessor. It's not for storing 8-bit numbers, as the 6502's other registers are. Instead, the register bits are flags. Yeah, so it's just a whole bunch of flags. 4 of the status register's bits are called status flags. They are the carry flag, the overflow flag, the negative flag, and the 0 flag. I'm almost finished. What do you need?
I was suggesting that we stop buying chocolate.
We stop buying chocolate?
Yeah.
Why?
Because we've been given too many chocolate that we don't even eat.
Yeah, but some of the chocolate we like a lot, and some of the other chocolate we never eat.
What about your sweet chocolate?
Okay, we can talk about this later.
Yeah.
So, I'm not going to talk badly about you. These 4 flags are used to keep track of the results of operations being carried out by other registers inside the 6502. 3 of the P register's other bits, called condition flags, are used to determine whether certain conditions exist in a program. These 3 bits are the interrupt disable flag, the break flag, and the decimal mode flag. That's that decimal mode flag we're always messing around with CLD. Yeah, so it basically looks like this. It's a bunch of flags. And so it keeps track of state basically for things like whether or not you have a carry overflow. So if you switch to a subroutine, um, those things you kind of say like, oh, I want to start a new subroutine, so I don't care about that. I'm going to clear those status flags, but I want to save them because when I return, I want the program to continue as if like I never affected the process status register, right? So that's why you would push the process status register onto the stack, and then before you return, you would um, not push it. You would take it out. You would take it and store it onto the stack, and then yeah, and then you would pop it or pull it out and store it back into the process register before you return. So that makes perfect sense. I guess I guess we are done for this addressing mode chapter. There was a previous video where we talked about the previous, the initial addressing thing, and it just got too long, so I couldn't finish. So if you did not see that, go look for that on YouTube, where we talked about all of these addressing modes: implicit, accumulator, immediate, absolute, zero page, relative, absolute indexed x, absolute indexed y, zero page x, zero page y, index, indirect, indexed, indirect indexed, and indirect. So, yeah, that all makes sense now, right? All right. 108. So we have 292 pages. We're about a third, a little bit over a third of the way through. And next one we're going to be doing is looping around and branching out. So that's pretty cool. We'll be able to like have conditional stuff and looping, which is very important. I guess branching out will be like conditions and like conditional logic. So super cool. And we have some, oh look, here's our byte directive that we didn't know how to use last time. All right, so that's it for today. And that's it for chapter 6, I think it was. Was that chapter 6? Right address, yep. Now we're going to do chapter 7. We'll be doing loops next time, calling assembly language programs from BASIC. I really don't care about that. Programming bit by bit, don't know what that's about. Math, fun, fun, fun. Beyond page 6, I/O and U. That'll be important, like reading from the keyboard and everything. Atari graphics. Okay, so it basically goes from what sounds like really boring stuff to graphics and advanced Atari graphics. So that's really, really cool. And oh, here, look, they do have an instruction set. Oh, yeah, this is perfect. Remember, we were looking for PLA? All right, so PLA, pull accumulator. That's perfect. Now I've solved one of my to-do list items, which is find the. Good thing I didn't, because I can't even read my handwriting. Find something of all 6502 opcodes. Find resource. Well, it's in the book. It's just at the end of the book. So that's good to know. And I wanted to find the Bug 65 manual also. Anyway, I'm going to end the video part of this right now, and I'm going to on stream look for this resource because then I can be done with it. So thank you for watching, and please like and subscribe. I have lots of other videos on other languages. I think we do. Like, we have one really bad one on COBOL, but we're going to do more on that. We have Nix, which is an operating system on Linux, a whole playlist. We did a lot of Nix stuff. We did a little bit of Rust, so you can look for that. We've done one on Godot. We've done a couple on Gleam, which is a cool language. I wrote a Discord bot using Elixir not long ago. I think that was the last video before this. I think that's it, right? Sometimes it feels like a lot, like two ADHD need to like focus a little bit more. So I think I'm gonna do one kind of like older language like this and one newer one like Rust until we get pretty far with both before I do spread out too much. Maybe that makes a little bit more sense, but sometimes I need a break and I need to do something different. All right, I'm totally rambling now. So, yeah, big difference from the beginning of this stream where I was so tired and didn't want to do anything. This is also like how I work too. Like, I never want to work, I never want to do anything. And then once I get started, it's so much better. So, thank you for being here with me and giving me a little bit of motivation to get this stuff done. I will talk to you guys later. Thank you. Bye.